Hi, and welcome to Algebra Examples. I'm Dr. Finch. Today we're going to look at an example that is going to focus on absolute values. So we see absolute values here. You'll recall, if you've paid attention in class, that absolute value of x, what that means is that we are going to take that number, whatever number that is, and it is going to output a positive output if that number is positive or zero, and a negative of that number if x is less than zero. So if we do a nice little graph of absolute value of x, we get something that looks like a V. So our outputs are always positive no matter what. We just have positive numbers coming out of it. We have five parts to this problem, and the fourth and the fifth ones are the ones that are really sticky. So we're gonna have fun with those. Let's start off with the first. We're trying to figure out if these are true or false. So the first one asks, if x is less than 5, does this mean that the absolute value of x is less than 5? And to look at this one, let's look at, I think a number line is kind of nice for this one. So if we look at a number line, and we look at a 5 on a number line, x is less than 5 means that we put an open circle there because we're not going to include 5, and we're going to include all the numbers less than 5. So those are all the numbers that fit that particular piece of information. Now, when we go to x absolute value of x is less than 5, one of the implications of our definition means that this can be rewritten as x lives between 5 and negative 5. So in this case, if we put our number line up, we'd have negative 5, we'd have positive 5. We are going to have open circles on both sides because we are not including the number 5. And we are going to highlight the information in between. So that's what absolute value of x less than 5 looks like on the number line. And as we can see, the two are not the same. One of them is going to give us a lot more numbers, this first one, than the second one. So this particular claim is false. It is not true. Let's go on to our second example here. We have absolute value of x minus 5 is less than 2, implies that 3 is less than x is less than 7. So we'll start off with x minus 5, absolute value is less than 2. And in this case, let's actually go through and use one of our alternate definitions. We are going to say that means that x minus 5 is stuck between 2 and negative 2. Isn't that lovely? So now we have multiple inequalities here, and we want to get that stuff in the middle to be just a regular old x. So we're going to take the opposite action. Instead of subtracting, we're going to add 5 to every single term there. And we get a negative 2 plus 5, which is a positive 3. Our negative 5 plus 5 cancel out, and we left with x in the middle. And on the right-hand side, we end up with 7. And that is exactly what we want. So this particular statement is true. All right, let's see what happens with this next one. We have x, absolute value of 1 plus 3x is less than or equal to x. And that actually is a mistake. That should be a 1, implies that x is greater than or equal to negative 3 halves. Oof, having x's on both sides, that would be a tricky thing, wouldn't it? So we're going to start off, and again, we're going to rewrite this. Let's rewrite it without absolute values as a larger thing here. Isn't that lovely? We can subtract 1 from each side. So that is going to cancel out our ones in the middle. And we end up with a negative 2, 3x, and 1 minus 1 is 0. All right. And the next thing we want to do is we want to divide out by 3. So we're going to do, we're just solving for x. Our 3's are going to cancel there in the middle. And we end up with negative 2/3 is less than or equal to x is less than or equal to 0. But you'll notice that this first part here does have the x is bigger than or equal to negative 2/3. So it is true that x is bigger than or equal to negative 2/3. Now, not all x are going to work for this particular function, but we do know that at the very least we can't go below negative 2/3 and pop something in for a solution. All right. So, challenge number 1. There is no real number x for which absolute value of x minus 1 is equal to absolute value of x minus 2. And the way that I was thinking about this, because, I mean, you can start trying to plug random numbers in, but yuck, that could take a really long time. So I like to go back to pictures sometimes. Pictures are super useful, right? And if we look at our basic picture of y is equal to absolute value of x, we can figure out what the pictures for each of these mean. So let's look at our first one, absolute value of x minus 1. So what this is going to do is we are going to take our x and our y there. If we plug in 1 for x, we end up at y is equal to 0. So we should have a point right there. If we plug 0 in for x, we'd get 0 minus 1, which is negative 1, but we take the absolute value of that. That's going to be a positive 1. Same if we put in 2, 2 minus 1 is going to be a positive 1. We know that our absolute value functions have that V-like formation to it, so we can draw the rest of our graph out. So this is a graph of y is equal to x minus 1 absolute value. Okay, I'm going to do the next one in purple so that we have some contrasting color here. Let's look at the absolute value of x minus 2. Now, notice the thing that I did first is try and find where the center of our graph is, that V point. Where is our y values equal to 2? And you'll notice here, when we look at this function, it should be fairly clear that if we plug in 2, we're going to get 0. So that is going to be where we are going to start off. When we plug in, let's say, the number 1 into our function, we get 1 minus 2, which is a negative 1, but we're taking absolute values. So it's going to be, there's our next point. And if we plug in 3, 3 minus 2 is 1. So here is, in purple, oops, our function y is equal to x, absolute value of x minus 2. Now you'll notice right here in the middle, right, our graphs meet, which means there's an x value that solves both equations. Now we can kind of look at that picture and get an idea of where that is. It's between 1 and 2. So let's try x is equal to 1.5, or since I'm not a big fan of decimals, I'm going to write this as 3/2. Improper fractions are easier to work with. I know your middle school and high school teachers are probably trying to get you to use mixed numbers instead of improper fractions, but when you get to college, trust me, it's easier with just improper fractions. So let's try that out. We'll try what happens when we plug that into our first equation. We get 3/2 minus, and 1 can be written as 2/2. So we get 1/2, and the absolute value of that is 1/2. Okay. And now for our next check. 3/2 minus 2. So that is going to be 3/2 minus, and 2 can be rewritten as 4/2. So we're going to get absolute value of a negative 1/2, which is going to be a positive half. So these two things are going to actually meet at 3/2 is where they're going to work. So the original statement that there is no x value is actually false because these two lines meet at x is equal to 3/2. Wow, that was a lot of work. All right, we got one more, and this last one is going to be a little bit tricky. This one looks really mathy in the way that it's written up. For every x bigger than 0, there exists a y bigger than 0 such that the absolute value of 2x plus y is equal to 5. Oofda, that's a lot. All right, let's try. And the first thing that I like to do is I like to try an example to just kind of see what's going on. So let's try x is equal to 1 because this says it says for every x bigger than 0, we should be able to put in something for a y that's positive that allows this statement to be true. So let's see if we can do that. All right, so if we did that, we'd have this equation, 2 times 1. So the absolute value of y plus 2 is equal to 5. And you know what? Instead of writing it as an inequality, we're just going to break this out into the two possible outcomes, right? Remember, we said absolute values are equal to the positive if it's already positive or 0, and the negative of its input if it's less than 0. So we're going to do a positive 2 plus y is equal to 5, and a negative 2 plus y is equal to 5. And we're going to see what happens. So in this first one, we can subtract 2 from both sides. We get a y is equal to 3. And in our second one, we get, actually, you know what? I'm going to do this a little bit differently. I'm going to actually times this by a negative 1. It's so much easier to put that on the other side instead of trying to then have to do that later. So up to you. You can always do that whichever way. They're going to get you the same answers. It's just a matter of what's easier. Okay, so now notice here we get a y is equal to 3. So if we start with a positive x, there is at least one solution that we can plug in for y that's giving us our outcome to make our equation true. So that's good. Now, is it going to be true for every single x out there? Let's try another example just to see what happens. Let's try what happens when we plug in x is equal to 2. Okay, we get 2 times 2 plus y is equal to 5. So that gives us 4 plus y is equal to 5. And again, we're going to break this into the two different outcomes. 4 plus y is equal to positive 5. 4 plus y is equal to, and again, I'm going to put that negative sign on the right-hand side just to make it a little bit easier to work with. So we can subtract 4 from both sides. Oh, and we can stop there because notice we have a positive 2, but notice now our y is 1. If we look back here, when we had our y is 1, or our x is 1, our y was positive 3. As we increased our x, our y value decreased. So we're seeing a little bit of a pattern emerge, but we're not sure. Let's try one more time, and perhaps we can get that y value to get smaller than 0, which is kind of what we're looking for because we want to see if the statement is true or false. Proving it's true would mean plugging in every single number, which could take some time, which means that If that is true, we'd have to actually create a written proof. And if you are in an algebra class or even a calculus class, you're probably not doing proofs yet. So chances are there is a counterexample to show that the statement is false. All right, here's our two different outputs. We subtract 6 from both sides. Y is equal to a -1. And subtract 6 from both sides. Y is equal to -11. So now we have x is 3, a positive, but there are only two values for y that work for this equation being true, and both of them are negative, which means that the original statement up here is false. It does not work. Now, the good thing is if you get something like this, chances are you plug in enough numbers, you're going to find a counterexample somewhere because your teachers are probably not expecting you to do full out proofs yet. So good luck with that. Thank you for listening.